So next we're looking at how to find the inverse of a function algebraically. First we want to swap those inputs and outputs. Because the inverse is that swapping, we did that graphically. And then once we've swapped those inputs and outputs, we're going to solve for y. That will get me into our function notation, so we can rewrite that y equals as f inverse of x. Let's look at our first example. We have a function f of x equals x minus 6 over 5. That f of x is the same thing as y equals, and so we want to swap those inputs and outputs. When I do this, I always swap using a different color to show something really important has happened. So that y equals is now x equals, and then y minus 6 over 5. We use our regular inverse operations to solve for y. So I want to undo the division. We're going to undo dividing by 5 by multiplying both sides by 5. That leaves me with 5x equals y minus 6. We can add the 6 over, so 5x plus 6 is equal to y. That has solved for y. Now we just need to write this in our function notations. This was a f inverse of x is equal to 5x plus 6. If we think about the domain and range, we started with a function x minus 6 over 5. Now that's a linear function. And you may not think it's linear because it has a fraction, but it is. There is no variable in the denominator. In fact, you could have rewritten f of x as 1/5 x minus 6/5. That's the same function. Now written this way in slope-intercept form, it might be more obvious that this is a linear function whose domain would be negative infinity to positive infinity, and whose range would also be negative infinity to positive infinity. The inverse of that linear function was another linear function, 5x plus 6. This function also has a domain of negative infinity to positive infinity, and the range is negative infinity to positive infinity. So linear functions are probably the easier ones to deal with, but let's look at a rational function in part B. So f of x is 3x over x minus 2, and we want to think about the inverse of this. In fact, let's actually start with the domain. I'm going to skip finding the inverse and go straight to this domain and range for a moment, because we know how to find the domain of a rational function. So if I were to do the domain of f, we know that the denominator cannot equal 0. X minus 2 is the denominator, so that would mean x cannot be 2. In that domain, it would be negative infinity all the way up to 2, and then 2 to infinity. That's the only value that's excluded from the domain. It is much more difficult to find the range of a function, a rational function. So I'm not normally going to ask you to find the range of this rational automatically, but because we can find the inverse, the domain of the inverse is the same as the range of that original rational function. So let's go into finding the inverse now. So this was an y equals, this is now going to turn into an x equals. So x equals 3y this time. The x and y have swapped places. So 3y over y minus 2. Again, still always put that in a different color just to re-emphasize that something big is happening. And as we're solving this one, we notice that we have two y's that we need to solve for somehow. The y's are on top and bottom of a fraction, so we really just need to get out of that fraction. And we do that by multiplying our denominator over to the other side. So that would make that x times y minus 2. is equal to 3y. If I divided by 3, I would still have y's on both sides. So if we're solving for y, we have to get the y's together. But I can't just subtract y over here to the right side. We have this multiplication going on, so I'm going to need to distribute. This would make this xy minus 2x equals 3y. At this point, we can get our y's together on the same side. And it doesn't matter which side we get them on. We could get them both on the left or both on the right. A lot of times students feel most comfortable putting them on the left side, but you can put them on the right. I'm gonna do what students normally do and move all the y terms to the left. So that would be subtracting 3y to the left side. And we can add the 2x to the right side. By doing that, we are getting at least the y terms together. I can't combine these, but I do notice that there's a common factor of y, so that I could factor out the y and make that y times x minus 3 is equal to 2x. If we divide both sides, because we have y times x minus 3, we can divide both sides by x minus 3. So this y by itself would say 2x over x minus 3. And there's our inverse function. F inverse of x is equal to 2x over x minus 3. We can find the domain of that function. So if we were looking at the denominator, the domain of the inverse, that's why I use this subscript so that we can show these things are separate. We have negative infinity to 3 union 3 to infinity, and this is because x cannot equal 3. So now if I know the domain of the inverse, we actually know the range of the original function f. And similarly, the domain of f is the same as the range of the inverse. So there's a little bit of new algebra that happened here where we were trying to get the y's on the same side so that we could factor out that y and get it by itself. That happens with our rational functions, and we'll see some of that same algebra skills show up later. If you want to practice that algebra, go ahead and pause the video and try part C on your own. If you're not ready for that, we can do it together. So in C, we're still going to swap our x and y's. This becomes an x equals a 5y on top and a 2y plus 6 on bottom. So x equals 5y over 2y plus 6. We still want to get y by itself. So to do that, we're going to have to get rid of this fraction. We get rid of the fraction by multiplying by that denominator. So this would say x times 2y plus 6 equals 5y. We can distribute on the left side to get 2xy plus 6x equals 5y. If we move the y terms to the same side, I could subtract 5y to the left and subtract 6x to the right. That would give me 2xy minus 5y is equal to negative 6x. By moving all the y's to the same side, we have a common factor of y that we could factor out. And that would make that y times 2x minus 5 equals negative 6x. At this point, we can divide. So y is equal to negative 6x over 2x minus 5. So the inverse function, we write that as f inverse of x, would be negative 6x over 2x minus 5. Now, if we had started with our domain and range, we would look at our original function and find the domain of f. We know the denominator cannot equal 0, so 2x plus 6 cannot be 0, which when we solve for that, we get x cannot equal -3. The domain of f would be -infinity to -3, union -3 to +infinity. That domain of f would be the same range of the inverse, and then we can find the domain of the inverse function because its denominator also cannot equal 0. 2x minus 5 cannot equal 0 would solve that equation into x cannot equal 5/2. So the domain would be -infinity to 5/2, union 5/2 to +infinity. That is the same as the range for the original f of x function. And we've got one more down here. The square root function, f of x equals the square root of 2 plus 7x. This one, we have found the domain of square root radicals before. So when we were doing this, we were thinking about the domain of f says the inside of that square root has to be at least 0 because we can't square a negative number. So the 2 plus 7x, that has to be greater than or equal to 0. We would solve that out, and x has to be greater than or equal to -2/7. That domain looks like a bracket, -2/7 to infinity. Now, if we're finding the inverse of this, we're still going to swap our x and y's. This becomes an x equals the square root 2 plus 7y. We want to solve for y, and it's inside of a square root, so the inverse operation would be squaring both sides. If I square both sides, that gives me x squared equals 2 plus 7y. I can subtract 2 from both sides, so x squared minus 2 equals 7y, and we would divide both sides by 7. So x squared minus 2 divided by 7 is equal to y. Our inverse function would look like x squared minus 2 divided by 7. Or if you wanted to write that as 1/7 x squared minus 2/7, you could do that as well. Both of those are the same function, though when we think about a quadratic function and what we started with, this radical function, they're not really mirror images or reflected images of each other. So if we looked at this graphically, this square root of 2 plus 7x would look something like this. It would start at -2/7 and go off to the right towards +infinity. The inverse function that we just graphed might be easier looking at this one, was shifted down 2/7. It would have a y-intercept of -2/7. And I'll do this as a dotted line. We would have an inverse function that's a quadratic function. And notice that that's not an exact mirror image of each other. In fact, if we only had half of that parabola, then it would be a mirror image. So this actually needs a domain restriction for us to describe it as the inverse function, and that's based off of what we knew about the range of f. So I found the domain first, but we could have also found the range because we know what a square root radical function looks like. A square root function here shifted left to negative 2/7, but it never went up or down. So its range was still 0 to infinity, which means the domain of the inverse also has to be 0 to infinity. So this inverse function needs to have that domain restriction saying, yes, this is the inverse function, x squared minus 2/7, but only as long as x is greater than or equal to 0. So you could write it as x squared minus 2/7 as long as x is greater than or equal to 0, or 1/7 x squared minus 2/7 as long as x is greater than or equal to 0. All right, so these domains and range of the original function f and the inverse function are really important. They are much more complicated when we think about a radical and a quadratic function. So we're going to spend a whole nother section just looking at quadratic functions and their inverses.